So what we're going to do is give you a very quick statement about the general business of amplitude analysis from ISS, and then boil it down to something very simple case where we can do a direct comparison of iterative as a machine compared to what the inverse scattering series does. Okay, so this was a keynote address this year in Abu Dhabi. I didn't actually go there, the video went there. I'm trying to reduce air travel. There was a similar on a different topic of multiple similar noise that aggravated Colombia. So there was a similar invitation for Brazil in August at some kind of SPGF. They just told me, you're invited keynote, no video. You're either here or not. And they're right. They're right. So it's not. And tiring, I don't have to tell you, travel gets tiring, and it's not healthy. Anyway, this was, so it talks about direct, indirect. This is an equation, a direct solution of the quadratic equation. If this wasn't derived in North Africa between the Greeks and the Renaissance, we'd be doing this today, South. We'd be doing some search algorithm. Yeah? Well, we have computers. What are we going to use it for? They'll search, fine. And we'll learn that all the x's are real. I mean, A, B, C are real. I want the roots be real. So here are indicators of indirect. Model matching, objective functions, cost functions, search algorithms, iterative linear, and we'll be talking about that in detail in a minute, and necessary but not sufficient conditions. For example, common image gathering problems, as an example. Well, first, there's a role for direct and indirect methods. We already mentioned that we have from a student Lin Tang who's with us, a way to try to indirectly determine near surface properties. Yes. That adaptive thing we're talking about, yes, is indirect. Yes. You understand? Any adaptive is indirect. You're looking for a quality, a property that you're trying to satisfy. You understand? We just don't rush to it. We want direct as much as possible, knowing that it'll never be complete, and then do some intelligent indirect to deal with everything you left out. Is it clear? We're not in some kind of holy war against indirect. This is being videoed. Probably lost my tenure just now. So this story you've seen, the inverse scattering series and all that, I'm not going to, you've seen this here, and this, I just want to point out one thing, or one important thing. The big deal about the inverse scattering series is it comes from an operator identity. And that operator identity, as I said earlier today, leads to a geometric series. And geometric series have inverse series. And that's the message. It's that simple. It's that simple. Taylor series, which is what we usually assume in terms of our model matching, yes? We have data at M, data at M0. We're trying to make them as close as possible by setting it equal to a derivative, a Frechet derivative, times delta M. That's a model matching method. And it's not crazy that they do that, because the Taylor series that's the first term of, it doesn't matter what are you going to do if you have more than the first term. We don't have a way to invert Taylor series. We have ways to invert geometric series. So it's not crazy. They take a forward problem linearly and update. Yes? It's just, okay. Anyway, this, this again is work I add for parameter estimation, isotropic 2D changes in Earth properties. The point is that you get a series. If you want, you get a forward series in other words, if you give me that G is G0 plus G0 VG, that didn't say what G is. It says G is whatever describes your field in whatever acoustic, elastic, electromagnetics, quantum, yes? It could be a matrix, yes? It could be, it doesn't have to be a scalar or something. It could be a vector and so on. In the elastic case, this is what it turns out to be. The forward series. The inverse series, to get that V, the V is a matrix. The first term, data G0, V1, G0. Yes? The second term, G0, V2, G0, just like we had here a minute ago, minus G0, V1, G0, V1, G0. In other words, that's just telling you what to do. You understand that? V1, V2, that's the prescription to get the linear and so on. The first term is not unfamiliar to people who do AVO or FWI if they're doing the elastic. The problem is, what they will do, from our point of view, is they might take one component and call it G times this, times that, and they get one component of that data and they start to deal with it and they update it. Okay? If you look at the second term in that direct solution, you'll know that's off base. Because the second term says, if you want this, these data things are coupled. You can't compute any one of these, the second order, without having the data matrix. Okay? So the direct inverse for the elastic tells you two things: the data you need and what you need to do with the data. Okay? Well, what are you going to do when you don't have the data? When Hyann, we were fortunate enough for her to be working with us. We couldn't tell the world, you're not going to do AVO if you don't have multi-component data. Yes? What are you going to do with Toad Streamer? You only have PP. So what Hyann did was, she synthesized. You're not going to put in for the data P, S, 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 okay, synthesize it, we said. I'm not pure, I'm an academic. Of course I'm not pure. You understand? That's not a joke. Every joke is only a slight extension of true. That's why it's funny. So what Hyann did was she took PP data and found these linear changes in lambda mu rho, and then used those lambda mu rho estimates and stuck them in formulas for SP, PS, and SS. If you do that, you will not get those, but it's better than zero. Okay? You're better to have measured. Yes? You understand? So Hyann did a whole series of tests with actual data and synthesized data. Yes? Understood? Yes? So, but it gives a prescription of what to do. Okay, so I'm going to leave that. Oh, one of the things that Hyann did with Doug Foster and Bob Keyes that got a lot of positive attention is afford the application of this. In other words, the way this was set up is you know this, you don't know that. You know this, and you don't know that. So that's a spatial difference. In other words, you want to know what the properties are spatially different from here to there. You can set this up, and this I think was Bob Keyes' idea, yes? You can set this up at one location. What is the temporal difference from one to the other, yes? At this, so they went through identifying those terms. The perturbation V was not between here and there, it was between now and then, yes? Understood? And then they did I ended working with them as an intern back then, a time lapse, and was able to, using that kind of, you can see, this is where we talk actual, it became current, yes? Instead of, you understand? Because it became now and then, a change in time. And there was a positive test. They were better able to determine a difference in pressure and velocity, yes? Than they could from linear methods. So that was a success. So I'm not going to go through that. Thank you, Abu Dhabi. Okay. So what I want to do is show you a, I mean, these were slides from Abu Dhabi. Okay, that's what it says there. Yes. So let me show you this next talk, which is a direct comparison of what the inverse scattering series says happens in the simplest inverse problem in the world. You send a wave straight down on a boundary, it comes back, yes? You get an R. It's not you got full bandwidth, and what does, and you have C0 and C1. You know C0 and you don't know C1. What does the inverse scattering series do to get that change versus iterative, yes? So just look at that, because it's not a difference of data, it's not a bandwidth where there's a Frechet derivative that, you understand? We're going to give them an analytic, them meaning the iterative linear, we're going to give them an analytic Frechet derivative, yes? And we just want to know what happens after linear, yes? So is that the